Okay, seems like okay, let's get started. I think recording is okay. Fine, and then so a bit about the recap of last time. So we talked about the conformal transformation last time, especially so d greater than 2 and d equal to 2 are clear difference. It's generated by p mu. I don't remember what I wrote last time. Maybe j mu. D dilatation everything. Okay. But instead here you have ln, n minus n, ln plus n, also n, where then ln is given by what was it? Minus c to n plus 1, then c, as far as we know. So this is the generator of conformal transformation. And then here equal to 2 case, the conformal transformation is given by just f of z, like this. F z equals f of z. So it's a homomorphic function. Whereas this one is a bit more. So yeah, as you recall, so what we need is like this way. Function x mu, function x mu, x rho, function x sigma, sorry. Like this way. So we need this is the meaning of conformal transformation. So lambda of x is a scaling factor. Scaling factor. Fine. That's the case. And then in the 2-dimension, for instance, it's everything homomorphic function. Z prime goes to z square, it becomes like maybe a shape. Z equals to z squared become like this. As you can easily see, so this grid, 2-dimensional grid become like this, but each intersection become the preserved angle. It's orthogonal. So intersect orthogonal. So this is z equals to 1 over z. Without all the line here, grid line becomes circle. Circle when you just how to say circle just intersect with the origin, because at infinity is mapped to origin. So if one of the z map z is one of the z map infinity to origin to infinity. Therefore, all the line straight goes to infinity. So therefore, it has to intersect with the origin, all the line. So that's what's happening. On the other hand, here z times absolute value z, so z bar, and take a square root. So in this case, that it's not a homomorphic transformation. So z bar, right? Bar include the anti-homomorphic transformation. So therefore, as you can easily see from around here, so it doesn't preserve angle. It doesn't intersect like a transversely. Orthogonally. So that's the transformation for 2-dimension. And another thing last time I wanted to show is this eigenmodel case. Okay, so this is just some video in YouTube. For instance, here left-hand side is less than Curie temperature, critical temperature. The right-hand side is a bit bigger than Curie temperature, and the middle is exactly Curie temperature. and they will scale like a scale to the IR. So infrared or like a low energy or large distance from now on. So if you zoom in, it looks like very similar, but if you zoom out, what's going to happen is here is looks really different. Okay, everything become outline. Everything become outline. But here, if you zoom out, everything becomes more like a random. So it's more like a magnetization is the 0. So black dot and this white dot become the same number. But at the Curie temperature, even if you zoom out, the pattern does not change. Okay. So that's a difference. So this means that this white means either like they prefer spin up or spin down states. I don't know. If you just said the white one is spin up, magnetization is like positive in this case. Here it's more like a black and the white dot become much more equal. So therefore magnetization is 0. In the middle, even if you scale up, scale in, zoom out, zoom in, the pattern does not change so much. Okay, so that's why people believe that it's describing the conformal filter. So this clearly means that this part and that left panel and right panel, the theory is not invariant on scaling transformation. So that at the beginning, the pattern becomes like this. So clearly the scaling zoom. So this is zooming the state which is zoomed in. After that zoomed out state is become this one white and that one is like a gray. So become gray. So therefore it's totally the pattern will change. So that it's not invariant on the scaling transformation. Okay, so that's this video. Okay, that's what I wanted to show last time. Okay, now fine, and let's move on to the. So last time we were talking about the radial quantization, and I think I made some cheating. So radial quantization. And state operator correspondence. So operator O and tau epsilon limit tau epsilon not epsilon tau e Euclidean time goes to 0 means the that action vacuum is the O. So this is the operator, and this is a state, and they are one-to-one correspondence because of the and then we consider let's see R and then R d minus 1 or d and we consider the origin and we just consider the sphere. I consider S d minus 1 sphere, and then you just consider a time radial treated the time, and that is the so becomes a cylindrical space. Like this way, and each slice is the space of slice is SD minus 1. This is SD minus 1 plus time like this way. And then the map between them is the subdivision. This compound transformation is a homework problem. I will post a homework problem soon, within a few days. And deadline is in 2 weeks. Okay, so that's how to find these compound transformations. Okay, and then what I meant is that so here the Hamiltonian of this cylinder space is related to dilatation on the this Euclidean glass space with radial quantization. So that's what I explained last time. Okay, ID. And then we define the state operator correspondence. So here it's just use the Heisenberg picture. So all the operator has a time dependence. So operator has a time dependence, what TE or TE or X time dependent, but state doesn't change. So therefore, operator O at the origin. Okay. At the origin, that axial vacuum will create the states in spatial sphere, d-1 dimensional sphere. So that's the state operator correspondence we consider, because I mean, everything is scaling invariant. So therefore, if you have a state and zoomed in at the origin, it just creates an object. That's the physical picture we have in mind. And then, so, okay. So on the other hand, last time I told you that okay, so let's do one by one. So, and then in this radial quantization, the P mu dagger is equal to what? K mu. And then primary state, you have a primary state characterized by like this thing, primary operator. Whatever you call it, it's okay. Primary operator is characterized by like this. K axiom at the origin. At the origin is equal to 0. That's the result. So now from there, so this is the primary. So this is the definition of primary operator. So using this one and use state operator correspondence. So K mu of O I is equal to O I 0 acts on vacuum. And this is equal to 0. Okay. So K mu acts on states that correspond to primary operator is annulled by the action of K mu. Okay, this is only true for primary operator, so not the arbitrary operator. So this means that this is the primary operator, and this is primary state. This is called primary state. By state operator correspondence. Okay. Okay. And then yeah, so the same logic HC or D acts on it, D or HC acts on the operator I. This will give you HI. And OI0 acts on the vacuum, and this is equal to DOI 0 of omega, and this is equal to delta I over So that's the transformation rule we have. So delta is this is the scaling dimension, a compound dimension, of operator. That's what we learned last time. Okay. So, and then, yeah, of course, I use the fact that so in here, so I use the fact that here, I use the fact that Ku omega is what? Can you have some vacuum? Is zero. Of course, the same thing. You see, some vacuum is that's the vacuum of the cylindrical. The radial quantization of vacuum is another part of the conformal. Okay. So now we consider the correlation function and so on. Correlation function and so on. But before that, we define. So this is this will define. It's a cat space, right? It's called cat space. I think cat space. And how do you define the Bragg state? So bracket, Bragg state. Okay. So natural guess is of course the omega and OI of tau e. Then we take a limit tau e goes to 0. So this is the natural guess to define the cat state space, but that's not precise actually. So that's not precise. So this is not the precise precise way of define that, because I mean, so here as I mentioned, so the 0 and infinity are related by x goes to 1 by x mu. Okay, x mu, right? So that's what we learned. Okay. So therefore, if you consider a conformal transformation, so in this case, or more precisely, so the 0 and the infinity are related by t equals to tau epsilon, tau e equals to minus tau e. Okay. More precisely, so r goes to 1 over r. Okay. That's a transformation rule. So we consider at this t or tau. This is tau e. So here you just consider tau e equals to 0, corresponding to radius r is equal to 1. R is equal to 1. And then, so this is the cylinder, and this is r d space. So under this transformation, so we have to be careful about how the operator is transformed. So that's what we need to understand. So operator OI of x, lambda x, acts on lambda to minus delta I, operator I of x. So that's how you define. So lambda. How do you define a conformal dimension? So that's how you get this factor, delta I, conformal dimension operator, or scaling dimension, whatever you call it, operator. And you just want to do the same thing for this one. Okay? Sorry. Another thing I have to say that you have to take a dagger. Okay? You have to take a dagger. Okay, sorry. Yeah, important things. Sorry. Okay. Okay. Okay, so that's the case. And the important thing is that, for instance, if you want to do the so this transformation into, for instance, 2-dimension, you get that z equals to 1 over z, and so on. Okay, then take the complex conjugate. Therefore, what you get is that, I mean, if you map 0 to infinity, at the cost of doing this one, so for instance, OI. At the cost of doing that is the essentially what you get is the z to the minus. Sorry, what am I doing now? Oh, sorry. I haven't shown you the how you get that under this transformation. So I didn't mention how to define the primary state in 2-dimension. That's another story I have to mention. Okay, so then before doing that, okay, so here what you do is as follows. So essentially what we need to do is that the operator, so if you take a dagger of this one, so in the so in the case of time, the Euclidean, so here, so you have an e to the minus h tau e is the time translation. And if you go to the Euclidean, it's a Euclidean. So in Minkowski space, the transformation is something like this one, right? Now, I times ht. Okay. So that's the Euclidean Minkowski time translation. And then since we take a dagger of this one, so you get the time translation with the minus sign, okay? Minus sign. But however, if you go to the t goes to infinity, is that so you need to multiply e to the 2 times IHT. Sorry, you have to multiply e to the 2 times IHT to make this operator goes to infinity. Okay. Otherwise, because I mean here, so if you take a conjugate, you get the minus sign, but we want to send this operator to the infinity. Okay, so therefore this has to cancel with this one, and in addition, you have to get the e to the IHT. Okay, therefore you have to multiply this factor, and going to the how to say Euclidean space-time. So what you need to do is that you have to put this t, or you have to set the t I times t. So I times t is equal to tau e and tau e. That's how you define the ket space. So unless you multiply this factor, all the correlation function become like you have an e to the minus 2h tau. Everything becomes 0, goes to infinity. So you always you have to cancel this factor, because I mean otherwise you always have at the cost of this taking conjugate, always you get this factor. So this is how you define the Brass state. That's what I mean. Sorry. Now, and the HC axon operator as the dilatation operator. So therefore, what you get is that essentially this is equal to limit tau e goes to infinity e to 2 delta I tau e, and then operator vacuum axon operator I dagger of tau e, and then efficiency is equal to this. So now HC acts on this OI. You get the dilatation operator, conformal dimension. So therefore, this multiplication is the same as this multiplication. That's what I want to do. Okay, so that's how you define the Brown state in this radial quantization. And so therefore, if you have a operator OI and take an inner product of like a OJ, this is equal to limit how e goes to infinity and e to the 2 times delta I how e in the vacuum in the OI how e again. Unfortunately, I'm running out of space. O times j how e and minus and then here in the vacuum. So that's what we need. So that's what you need to do. To define the inner product. To define the inner product of this heuristic. Okay. So at each circle you can associate. So that in quantum field theory and Hamiltonian formalism, so at each circle, each spatial sphere we associate to the some heurispace of theory, and in the heurispace theory. You need to introduce some inner product. Always, so in physics, we always consider heurispace. You have an inner product, okay? And that's how we define the inner product, okay, of the heurispace. Okay, so that's so this is the inner product in heurispace. That's how we define the inner product. Okay. So, and moreover, so in physics, so in the CFT, it's bounded. It's a bounded. So everything is positive definite. Okay, so unitary CFT. So the important thing is unitarity CFT. So everything, all the state, so we impose positive definite. Okay. So that's what we impose for the unitary CFT in the heurispace. That's an assumption we impose. Any question at this moment? Okay, and now we take a look at a bit more about the structure of this heurispace. Okay. Fine. So first claim is that and recall that so if you have an operator OI of 0 over x or whatever, OI is a primary state. Then primary operator of scaling dimension, conformal dimension, delta I. Then P mu acts on OI is it's called descendant. That's what we learned last time. And what is the conformal dimension? Is what? What is the conformal dimension? Okay, down to I. Okay, so So if you act p mu many times, it just increase the component dimension. Okay. So this is yeah. Anyway, so you can act many operator mu1, p, mu2, act on OI, and so on. So this is called level 1, descendant, level 2, descendant, people like this. Okay, so the number. And then, of course, composition become like change like this. So, okay, and then if you act on k mu, you just go back to the k mu. Appropriately, you just go back to the. You just now decrease the level. Okay, and if you act on k mu on all I, it becomes. It's just another. It's just another. Okay. It's just another. That's the definition of parameters. Okay, and so everything is this level is the how to say the filter. Oh, okay. So all the grading is given by is the HC eigenvalue of HC Hamiltonian. Okay, so we just consider the Hamiltonian acts on the state diagonally, okay, on the state. Okay. The first claim is that the first claim is that the so suppose HC, so the Hamiltonian of cylinder has this discrete energy spectrum. So discrete means that it's not continuous. Then the Hilbert space is any state is spanned. Then the claim one is the all state. Any state. All states are either primary and then or descendant. It's descendant. Or it's a linear combination, but a linear combination. Okay, maybe more precise statement is a linear combination of. Okay. Because here space is a vector space. You can always have R linear combination of primary and descendant. That's correct. Okay, let's prove that. Okay, let's prove that. So suppose you start with the operator. Consider O is a primary state. Wait. Let's see. Okay, suppose O is a state of component dimension. Delta 0. Then one can create a state O prime such that the O minus sum of primary and then delta psi p operator, delta psi p, and then bracket psi p plus psi p and k out, and then psi p, kp, and psi p, and p acts on psi. That's considered. Let's consider such a state. So what is the property of this state? So here, so what's the psi p? Psi p is all the states. Okay, and psi p are the primary state. So primary states of component dimension is less than delta 0, less than or equal. Let me think. Okay, less than equal. All the primary. So therefore, and then so such a P only exists finitely many. Such a primary state. Because I mean, if you consider energy spectrum Hc and you have 0, I would say it's bounded by 0. So, and you have a delta 0, which is the component dimension of O here. Component dimension of O here. So, the primary state with the component dimension delta 0, it's just finite length. So therefore, it only has whatever. Delta P1, delta P2, delta P3, delta P4. There are only many primary states which has a component dimension less than delta 0. Otherwise, if the energy spectrum is not discrete, if it is continuous, you can have infinite many primary states in between. But otherwise, if the energy spectrum is discrete, you can have only finite many points in the middle. Okay, because it's discrete. So therefore, there are only finite many sum you consider here. That's important. Then let's consider the O acts on O prime. Okay, or maybe let's consider psi p acts on here, right? Psi p O minus what was that? Sum of P prime. Then what we have is that the delta P prime psi p. Okay. Is it okay? Is it okay? And so that is coming from here. So if you add psi p prime on here, you just have an inner product of psi p prime and psi p. That will give you delta pp prime. Okay? Is it okay? Delta pp prime. So psi p prime psi p is equal to delta pp prime psi p psi p. Okay. So therefore, this one cancels with this guy, the denominator. What's left is this one. Okay. And if you add the psi p prime on here, okay, p acts on p. So this is psi p prime axiom P is a momentum, of course, here. Okay, is that okay? So this subscript P is primary P, and this P is a momentum P. Axiom primary is equal to what? On the left, 0. So this is the K axiom psi P prime dagger, right? Dagger. If you take a dagger, like K and P are related by dagger. Therefore, K axiom the primary is equal to 0. Okay. So therefore, you can ignore the third term. So therefore, this is equal to 0. Now I put the P and P prime the same. So therefore, this is orthogonal. O prime is orthogonal to any primary field P. Psi P. Okay. Moreover, operator axiom of P. Okay. So this is equal to O minus sum of P and then O psi P and O, and then here you have a normalization psi P. That's the first term. The second term is that they and then second term is that the psi, the operator of P psi P and psi P K O. I mean, yeah, psi P K P psi P. Okay, so that's all true. I mean, you can consider many. This K and P are the some symbolic way of writing. This P axiom psi P is a something P mu1, P mu2, P mu5 axiom psi P. You can consider like this way. I mean, so here is just symbolic way of that descendant. I mean, this is the meaning of it. This is descendant, this is primary. Okay, that's what I meant. It's just a linear combination of descendant and primary state. That's what I want. Okay? So then, so this one. So here we just assign. So this means that so you just consider operator times identity operator O, and then O. This is equal to this one. Because we just insert the following operator. This operator, one operator, is what we usually do for quantum mechanics. So it's just one is the all possible state with appropriate normalization. So usually you put that all possible state. One is equal to all possible states, okay, which is orthogonal to each other. Okay. This is what you do, right, in quantum mechanics. So here, if you look at this one, so this part is a primary state, and this is descendant with appropriate normalization, because this is normalization. Denominator is just normalization. It's not so important. It's indeed identity operator. It's yellow, corresponds to this one. Okay. So therefore, this is equal to 0. This is equal to 0. Okay. Therefore, operator O prime is in fact orthogonal to any primary state then operator. O. Okay. So they are all orthogonal. Okay. Suppose Okay. Suppose such an operator, so this is all prime. This all prime are orthogonal in all the state in H, Hilbert space. That's what I showed here. Suppose all prime, so we want to say this one is equal to all prime is equal to 0. We want to say, in this case, so we want to show. This means that the all prime is 0. So it's just nothing. And it's shown by contrarily. So this show by contrarily. Assume, suppose all prime is not equal to 0, some non-trivial state, which means that it's contrary. Suppose this one, and then we want to see some contradiction. Okay, we want to see contradiction. Okay, and so all prime, okay, so all prime, so let's act K prime. So many times, if you act K mu1, total K mu2, total something like a K mu I acts on all. If you act sufficiently many K, this will give you, this will annihilate. Eventually, this is equal to 0, because I mean it's just a linear combination of state. What is it? Did I already? How I define operator? Oh no. So here you have us. Okay. Yeah, sorry. So this operator, this all prime has some. Okay. So the operator all prime is the some conformal dimension under HC, so the operator, the term of the operator all prime, and which is how to say bounded. It's bounded by bounded. It's a finite body, right? And if you act K many times, it just decreases the delta prime. Okay, and eventually it hits to 0. If you just decrease one by one, okay, and finite many steps, it hits to 0. So then therefore it should annihilate. Okay. So therefore, if you act sufficiently many K acts on operator on all, you get the vanishing state. But this contradicts with the following thing. So this contradicts with the all primes also to all the states, because the okay, yeah. So this contradicts the okay. So let's define this is equal. This is equal to psi. Okay, and then this should be equal to. Sorry, I told you wrong. what I'm trying to say. The center. Okay, so okay, fine. Okay, so summation event you get 0, right? So this means that yeah, you get 0. But I mean the last step, if you just define that, so this is the mu I step, the last step, this is non-trivial thing is non-zero. So we assume this is non-zero. Then this is equal to primary state. Okay, do you understand what I mean? Okay. That's what I want to say. So if you add I times k mu I as an operator equal to 0, so that the one step before is non-trivial state. And since you, which is annulled by one more action by k, which means this one is primary state. Okay. So this means that the psi. So it's a non-trivial state. Psi and psi is non-trivial state because under the assumption primary state is non-zero in the product, and this is equal to what was that? So this k mu 1 acts on k mu I minus 1 O prime, and then acts on psi. Okay, so that's non-trivial. Okay, and this can be understood as the operator O prime acts on k mu 1, not k mu 1, p mu 1. So the acts on p mu I minus 1 acts on phi. Acts on phi. Okay, but just k is the dagger of p, right? Therefore, if you bring the brass state, k action of brass state to the K's state, it just becomes the p action. Okay, it's just p action. But now this is just descendant. Phi is the primary state. Now phi, this one is primary state. Primary state. And the O prime, okay. In a product with this is descendant. Phi is primary state and p acts on many times on primary state. This is descendant. It's not equal to 0. So therefore that is contradict with the assumption all prime are orthogonal to all states, okay, in H. So therefore it's contradiction. But therefore it has to be this one. It has to be this one. So this means that the operator O prime that are orthogonal to all the states written by any possible like operator, O is a Hilbert space which is written by primary state and then its descendant, which is the orthogonal to the any primary state and descendant, which means that the operator should be 0. So this means that all states are linear combination of the primary and descendant. That's correct. So that's the grade 1. That's grade 1. We show. Any question at this moment? Another crane. Let's suppose. So phi is both primary and descendant. Then this means that they are crane 2 psi has to be zero. Has to be. It doesn't exist such a state. That's what I want to show. Okay. Both primary and descendant states means that the primary means that the k mu acts on psi is equal to 0. That's the definition. Okay? That's the primary state. Descendant means that the psi can be written as a p mu of some state phi. Okay? That's the descendant. Okay? Then, using this property, one can show that the psi. Oh, did I erase? Okay. Psi and psi is equal to over psi and then p mu of phi. Okay, and this means that the k mu acts on psi and phi. Okay, but now we know that the k mu analyzes psi. Now for this is equal to 0. And I have to mention that so that the Hilbert space is Hilbert space positive definite. Means that any state of psi and psi is bounded by this state by 0. This means that equality only holds so equality only holds for trivial state. It's just trivial. So this one means that this means equality holds both psi, phi is equal just trivial state. It's just one. So that's fine. So now here I use the fact that since the inner product equals to 0, so the output state is trivial. The output state is trivial. That's one. Fine. Another property. So I think so that's claim 2. So another claim is what? Okay, another claim is that the scalar operator of a scalar operator OX with of component dimension 0. Component dimension 0. Delta is equal to 0, then this operator O of X is just identity operator. It's just one of this. Okay. So to show that we want to show the state operator correspondence, so we want to show the as follows. What should I show them? What I want to show you. So if you consider it, okay. So what I want to show is that the P mu of all analytes are analytes. So this means that it's independent of x. It's independent of x. This should be 0. So this should be 0. This means that so I want to show this one. I want to show this one. Okay. And to do that, I think that I use this one. Again, P mu operator, and then operator. So I use the again K mu, okay, operator. Sorry. Scalar primary operator. Primary method of works is this one, and then what I want to show is that the O of, so this is K mu, and it's minus, it's equal to minus of P mu and K mu times 4, and this is equal to 4. 2pi delta mu plus j mu. Like this way, and some 4. Okay, so that's what we have. This one, and this is equal to, and this is equal to, its rotation does not change. Rotation does not change anything. Does not change the any inner product. So you can ignore this one. And if you consider this, think you have a 2 delta mu delta O operator O acts on equal to. So this J mu is the rotation. Rotation does not change the inner product of O and O. If you consider the conformal filter, so the inner product, the inner product of the Hilbert space is invariant on the J. So therefore, this acts trivial. On the other hand, D acts on O by scaling transformation delta O. And we know this delta O is equal to 0. So therefore equal to 0. Therefore, which means that the P acts on operator is equal to 0. So therefore this is the operator is just a scalar multiplication. It's just it's independent of x. It's independent of x. Independent position. So therefore it has to be an identity operator times some scalar multiplication, C or something like that. But this scalar multiplication, this is just number. Okay? Just number. So you can always scale operator by number. Therefore, it's just identity operator after scalar multiplication. Okay. So that's another thing. Then okay. So actually, so we can just relax this. This one is just any scale operator with conformal dimension down equal to 0 is okay. So this can be relaxed. Can be relaxed. Can be omitted. But I'm not gonna show. I'm not gonna show. It's also difficult to show. That's one thing. But we can omit this relation. Okay, so we just show three claims. One is that everything written in terms of primary states or descendant. The other is there is no state which is both primary and descendant. Okay, there is no such a state. Okay, and if component dimension is 0, which means just identity operator, scalar multiplication. That's it. Okay, so that's the case. Any question at this moment?
Sorry, does that mean the operator corresponds to the vacuum?
Yes. Wait. Yes, I think so. This one. So yeah, state operator correspondence. One is the vacuum. That's right. That's right. But another state operator. Yes, that's right. So another state operator. This identity operator is just vacuum. Another state operator. I mean, it's very. This is the case, right? This is the case. Identity operator acts on vacuum is just vacuum. So therefore, by state operator correspondence, I mean you can take limit tau equals to minus infinity, but it doesn't matter because it's in better time. Yeah. So I don't operator correspondence. Fine. Any question at this moment? Okay, if not, I think it's a good time to take a break. And I will move on to some correlation function a little bit. Okay, so let's take a break. And if you have a question, just tell me.
It's just showing that it is all the same in every position that is here.
which means scalar multiplication. It's just scalar multiplication.
I mean, it only shows that this operator is all the same thing.
Yeah.
But this operator is an operator that is a local operator.
No, it just gives you scalar multiplication. Because it's an independent operation, so it's just scalar multiplication. That's only possible.
And also, I have another question: why can't we have an operator that is not annihilated by K?
What?
I mean, why we can't have an operator that can't be annihilated by K?
What do you mean? Primary space can be another.
Yeah, I mean, if why we can't have an operator that can be annihilated by within the case? Why do we? For example, can we have a state that after any many case that it still can go to zero?
What's the question? Can you repeat it? I think your question does not make any sense.
We have such a state that is
infinite
not
case.
infinite, just a finite case, just no matter how many cases I act, it still can't go to zero.
Because it's bounded. The spectrum is bounded.
Okay, so
it's a discrete. So if psi has a conformation, finite not K decreases.
Okay, so there must be a lower bound.
0 is a lower bound.
Oh, okay.
What? Okay. That's a good question. In T of V, X of V of what? It's just like this. That's true. That's true. That's a very good question. That's true. That's true. That's definitely true. So this should be the key.
I think the intention the scalar field is not primary. This condition primary.
Wait. So what's the monic function of that? It's something like it's just plus something. Plus log 0 equals to 0 is minus 1, which should be doesn't create anything. It doesn't create anything. By stated or plus one, the x of v does not create anything. Then here it's just equal to 0 is just 0. Well, actually, it's just one thing. But it's not experience or everything. Yeah, of course, anything wants, everyone doesn't matter. Everyone is minus 1. Okay. Yeah. But everyone is equal. So it doesn't matter. So x of t in the state algorithm plus 1, it doesn't map to any in this 3D scale. So that's why it's state. Please grab the state. So this is not operator in scale algorithm. It's not operator. Yeah, so this is primary and this is another set of Conformal distribution. X of Z is not open. It doesn't create any stable fields. This one. It's okay if you want to come. You don't. Okay, shall we resume? Okay. So far. So here. Okay. Anyway, I don't care about the. Are there same students in the audience? Where are you? If you are same students, please raise your hand. No same students? Okay, since their own CFT course, their own program. I don't know. It's okay. I mean, it's okay, but no same students. Since okay. Fine. Okay, let's review. So let's consider operation function from now. Operation function. I mean, I think think many of you already learned QFT, but it's okay if not. It's just some constant field and time order implicitly. Okay, like this way, and then consider like 5 over x1, over n, and 4, like this. Okay, so this is the final path integral. This is the final path integral. Path integral, and this is just action, and this is called time order product. Okay. Time order is the here x1. I mean, so you have to put the operator in such a way that T1, T1, T2. I don't know. You don't know how to define. Sorry. And so on. Like this way, so you have to impose like this kind of condition. That's a time order product. But that's not so important. I mean, just that that's not important. So we'll just compute this correlation function by using conformal theory. That's what we do. So, the definition of that, we don't have to perform the path integral first of all. And sometimes, often conformal theory, this S is not known. So it's just that, I mean, it's just conceptual way of understanding the correlation function, but it's a meaningless definition. Even physicists, this kind of like computation only can be done only for free theory. For free theory, I mean, one can perform Gaussian integral and so on to perform this correlation function, but for interacting theory, or moreover, I mean, many QFT, this is not possible to compute. So it's a meaningless definition. I mean, it's just conceptual definition. You just put that. So it's just conceptual definition. You just put the operator in the time order way. So let's consider this is time order and the operator x, and the operator. It depends on how you define, but let's consider this is definition at this moment. Xn, and then you just consider all possible field configuration you can have in this space-time, whatever field configuration. I mean, just get a correct way of writing project in action and perform all possible configurations. This integral is not mathematical rigorously defined, first of all, and so even if you define, you cannot perform this integral unless the free theory. So it's a meaningless definition. Even though it's just conceptual, it just gives a conceptual definition, but it's anyway. You don't know how to deal with it. You don't know how to do it. Okay. Let's consider the order Gaussian. So we know that if Q is a symmetry of whatever system QFT, or CFT, whatever CFT, or CFT. Then 0 is another by Q. Okay. So this is schematic way of writing this one. And so we know that the Q acts on 0 is 0. Okay, we know this is 0. But this can be understood as the Q acts on O1, O2, ON, 0 plus O1, Q, O2, sorry, O3, ON, 0. Here. And plus O1, O2, Q, ON. That's that. So this is called Orthogonal identity, like some simplest versions of Orthogonal identity. And now we consider Q as a general conformal transformation. Okay, now we consider Q is the general conformal transformation, and consider one by one. And we consider, so this is endpoint, so this is called endpoint correlation function. Endpoint correlation function. Alright. Okay, and then we consider n, so this is 1 point, and 2 point, and 3 point correlation function. So let's consider this case first, 1 point correlation function, and then we just consider 0. So 1 point correlation function 0, operator of x 0 equal to 0. Okay, so that's the we consider the case. And sorry. So we consider this correlation function, and then we want to show this is 0 actually, or yeah. We consider this correlation function here. Here it's just some scalar operator in of component dimension delta. So since P here is the, so this is 0, this is 0, and this is equal to I times 0 partial mu of I of x and 0 and delta. Okay, that's the case. So this means that this guy is constant. This man is constant. This is constant. And what we usually do is that the and another thing is 0 is equal to 0 d and operator x 0, and this is equal to I times x mu function mu times delta I, and 0 or I of x and 0. So this is the case. Yeah. And since we know this is just constant, so delta mu x on this guy is the 0. Therefore, this means that the delta should be equal to 0. And we know that delta equal to 0 is just so delta 0 means that this is only can be possible for identity operator. Okay, identity operator. So this is a, yeah, this is 0. So therefore this means that the 0 x 0 is non-zero when all x is identity, otherwise 0. Okay. So that's what you mean. I think this means a constant. Okay. Okay. But if this is a constant, a non-zero constant, that if delta is non-zero, this cannot be 0, right? Therefore, if this is an identity operator, this can be non-zero. But this quantity or whole quantity is non-zero. But otherwise, it has to be 0. Okay. Do you understand? That's the property of 1-point function. Let's move on to 2-point function. Okay, this means that there's another implication of this means that this means that if it is this case, this means that this is equal to 0 and O. So this is O actually, not 0. It's 0. So O is the vacuum. Sorry, here I use 0 instead of omega. This means omega. Sorry. I think I should use. I think I'm always use the radial quantization. So I think I should use omega instead of 0. Now I'm going to use omega. I think I will change the lecture notes. This should be everything omega. It's a radial quantization. This is omega. Sorry. If you take a note, you should change. There's So this is so this means that the vacuum is the orthogonal to any other operator. Orthogonal to any other operator. Okay, 2-point function. 2-point function. 2-point function. Suppose we consider Gij omega O I x1 O J x2 and omega. So we consider such a correlation function. Okay, and then we do the same exercise. So EV commutation ratio, this one will give you the following thing: 0 is equal to function mu1 function mu2 acts on Gij x1, x2 is equal to 0. Okay, so this means that the G is a function. This means that the G is a function. Gij, two-point function, the function of the distance is equal to function of the difference of 2 points. So it's just a function of x1 and x2. This means that it just only depends on difference between these 2 points. Okay, what else? So let's use anything. So J. So this one will give you what? We just give you is equal to x1 acts on Gij x1 minus x is equal to 0. So that's the case. So this means that it is in, okay, it only depends on its no factor, and this means that it's invariant rotation. This invariant rotation means that invariant translation means that even if you change this way, like this way, it only depends on the distance, and its rotational difference means that it depends on absolute value. So this means that it only depends on absolute value. Absolute value. Okay. And now we consider D on this one equal to 0. I mean, it's just an exercise for conformal transformation. So this means that the Gij x1, x2 is equal to some constant times x1 minus x2 plus delta I plus delta j. Is it okay? Do you need a calculation? No. I think it's totally fine. Okay, is it okay? Do you? I mean, this one is just a square root x1 minus x2 mu, x1 minus x2 mu. And then a constant, and then times delta I plus delta j, and you just add x1 x plus x2, sorry, x1, x2 dot. So you just act on it. Okay? Then what you really get is that the what you really get delta I plus delta j and minus I. Is that's what you need to get. I mean, it's easy to see, right? You guys can easily see it. I mean, if you do the time derivative of distance, you get the whatever, like some power you will get, like it become extension square. It become extension square with this factor. But now we have marked the x1. But here you get the upstairs you have like something like a x1 minus x2, 2. I don't know. Okay. Now I plus delta j. And what we have is x1 minus x2. And then essentially we have x minus x2. That's essentially what you get. And then you count down with this guy too. And then it's okay. That's what you get. And so therefore this will be size. This will be size. It's easy. Fine. And how a special conformal transformation? So can you listen like this way? So do you remember? So can you act on this one? I mean, it's the here. So here, do you remember what's generated? I don't even remember. X dot sigma. X dot sigma. It's a linear combination of this one. And the other thing should be what? Yeah, some x squared minus mu. Something. I don't remember how. So that's what you get. I think that's it. No, I don't. You print out this part. I think. See that? Okay, I don't know. You can print out this part. Oh, yeah, it's okay. I think it should be 2 and 1. 2 and 1 is fine. So if you act this one, and here, just order derivative acts on this one is you get 0. Order derivative acts on this one is you get 0 because then p mu. Wait, what's p mu? Yeah, p mu analysis this one. On the other hand, here, what you get is that the x dot. What's that? This one, you get x dot here, you get this kind of combination, delta I and delta j. Hey, if you do the computation correctly, you get the delta 1 minus delta 2. So equal to 0. So this means that the whole conformal measure has to be equal. Okay, so that's okay. So therefore, at the end of the day, so what you get is that the false. At the end of the day, Gij x1 and x2 is equal to x1 minus x2 delta I plus 2 delta. Okay. 2 delta CH. So that's for delta is equal to delta I plus delta G. What you get from this calculation. Any question at this moment? So this is the consequence of conformal transformation. Any question? So now, so what's this quantity, Cij? What's this quantity, Cij? This Cij. So we recall the point. Is Cij. So let's consider the following quantity. So the operator OI, operator J. So in the Hilbert space. So in the product of this OI and OJ, this is equal to limit of time equals to 0, e to the 2 delta I tau e and omega O I of x or tau e like this way. That's what we have. Okay. But we know this guy is equal to limit tau e goes to 0, e to the 2 delta I tau e. Okay. And this guy is equal to I of x of 0. Sorry. So this is equal to so here it's just so that we need to do a scaling transformation. So we need to map this RD space, and you have sphere and origin and so on to S1 plus RT cross SD minus tau. So it's not in space. Like this way. Okay, like this way. Okay, and then here we need to do this. I mean, you can put the radial direction here. So radial direction here is x is something like this. This time direction tau e. Like this way. So we can put like this. Okay, and then eventually we put the operator O J of minus tau whatever. The position OJ into the 0, and then here OI is mapped to infinity. So this means that here you have operator of I is minus tau, and operator here, operator here, J of tau p is like this way, and then just separate like this. And if you mark like this way, you just do like this. And this mark is given by. So the mark is given by x is equal to e to the tau e to the tau. Okay, so like this. Therefore, if you translate it to the language of RD, this will become like this one. X to delta I, and then x to the 2 delta I divided by Cij. And this is equal to, and the x goes to infinity. X goes to infinity. From here, from this analysis, and this is equal to Cij. Okay, that's what we need. So I just use a map between. So this where R direction is also okay. I mean this is the essential R. It can be called R, whatever you call it. I mean R or X or it's whichever is okay. It's just radial direction. R is equal to e to the tau e if you use this relation. So we know that this correction function is equal to R to the order of Cij, essentially. Okay. Whichever x is also both okay. And this is equal to Cij. So therefore this guy is in fact just an inner product between OI and OJ in Hilbert space. Okay. That's what. Okay. So in the numerator here is just inner product in Hilbert space. Okay. And also this is called this guy is called no. Sorry. That's okay. And when daughter Okay, and anyway, so this one is the homological So this is called homological metric. I mean, I would say why it's called homological metric like. So this one is like in due course we will understand why it's called homological metric. It's coming from C theorem, the homological theorem, which will appear like 10, lection 10 or something like that. I don't know when I talk about homological theorem, but eventually we will understand why it's called in two-dimensional. And often, so as I mentioned, so at the first lecture, okay. So if you have action, whatever Hamiltonian or whatever the theory you have, the theory can be perturbed. QFT can be perturbed. CFT, okay, CFT is not. CFT is perturbed. Perturbed by the word D, the action D, dx, gi, or I. Okay, it's kind of like if you add the action on this. In this coupling term, in the operator, you can perturb the field. And then, as I mentioned, so here you have the the theory space, we have a free theory CFT, and if you perturb this one, it just flow to some, maybe it just go to non-trivial fixed point and so on. CFT1, CFT2, and so on. Okay? And this is the other direction and so on. So this is the relevant deformation and so on. In the middle, you can have some QFT, but not CFT, and then that if it is a nice case where a function vanishes and so on at the IR incorrect, you runs into another CFT and so on once it's returned. However, the scale dimension, component dimension of OI is equal to OI down I is equal to D dimension in the sense of the quantum mechanical. So even if you include the quantum correction, if it is this guy, GI is the dimensionless. Okay, it's a dimensionless. So if it is quantum mechanical, it's true. Mechanically, it's true. This GI is dimensionless. Okay, dimensionless. In this case, this is called exactly marginal. Exactly marginal motion. So even if you turn on this term, it stays a conformal. The theory will change, but it's still conformal. Theory will change, but it's still conformal. Because it doesn't have any scaling dimension. Okay, at the quantum mechanics. Okay, so therefore. So in this case, this is called exactly marginal deformation. In this case, this guy is called exactly marginal deformation. I mean, classically it's called marginal deformation. Classically, this is true, it's called marginal deformation. But quantum mechanical, this just ordinary relation between scaling dimension and then it will be quantum mechanical modified. That's called anomalous dimension. I mean, anomalous dimension. But even if you take it as quantum mechanical, if this is true, quantum mechanical, I wrote quantum mechanical, then it's called exactly marginal. Then, even if you deform theory CFT1, and then you deform to whatever by the theory, DDX, GI, and the OI, by adding this action, this term, interaction term to the action, stay the conform, stay conform. So therefore, this deformation often called conformal manifold. Okay, conformal manifold. So that since at some nice deformation, the theory still conform. Okay, even though theory will change, but it's still conform. Okay, that's why it's called conformal manifold. And this Cij coming from this exactly marginal operator will give you the metric. So OI, OJ. So both are exactly marginal. Exactly marginal. Exactly marginal operator will give metric on this conformal manifold. That's why this logical metric is important. Anyway, so that's another story. Anyway, so if you learn the CFT very deeply, this kind of like a conformal manifold, Zamochkov metric, and so on will become very important topic, and still like some active research topic even now. Anyway, so that's So it's just the linear integral product in Hilbert space, but it just gives you some very important information. That's why. Fine. Let's see. So this is 2-point function, and then after that I will quickly move on to 3-point function. 3-point function. 3-point function. So we just consider G, I, J, K, x1, x2, x3, which is equal to x1, or x2, or k, x3. So this is a 3-point function we consider. The situation is something like this. Or x1, or j, x2, or k, x3. And then, of course, this time translational symmetry is there. So that's what essentially what we need is it just depends on the relative distance between them. Okay? Of course, there. So now I write down relative distance x1, 2, xij, xi and xj, where I and j is the boundaries. And then of course I think I will j. That's my definition. And now we do the same step. D. This will give you the following thing. So x the same exercise. Well, unfortunately, erase no. C plus delta C. This is equal to x on the what this Gij x1, x2, x3 is equal to 2. So that's what you get. From there, one can just consider so from there, if you write down the Gij is the x1, x2, x3 is equal to x1, 2, a, x2, 3, b, x3, so I already mentioned that this absolute value. I don't need absolute value. Sorry. What I'm trying to do is that the x1, 2, a, x2, 3, b, x3, 1, c, like this way. If you write down all possible combinations of a, b, c are some integer power, which let's assume is polynomial. And then from this relation, what you get is a plus b plus c is equal to minus delta I plus delta j plus delta k. That's what you need to get from this construct. So that's what you get from this from here. And then this is homework. It's a tedious, but you can show it. One more problem. if you do the k here, as from this is equal to 0, it's conversion function. From here, what you get is that the GIJK x1, x2, x3, GIJK, and x1, 2, delta I, plus delta J, plus delta K. Delta x2, 3, delta J, plus delta K, minus delta I, x3, 1, delta 4, K plus delta I minus delta J. That's what you get. So everything is just difficult. I think it's just if you use the transformation rule for special chemical transformation, one can show. Okay, so that's how it works for 3-point function. Okay, so this 2-point function and 3-point function is completely determined by conformal transformation. At least depends on the position of the operator. But important emphasis needs to be added. How to say to determine this guy is difficult. Usually difficult. Usually difficult to determine. This guy. So conformal symmetry tells the 3-point function of the operator should take this one. But this coefficient depends on the choice of operator OI, OJ, and OK. Depends. Most of the cases, you cannot determine CIJK, even CFT. I mean, given the operator, 3 operator, to determine CIJK is very difficult. But very difficult for usual CFT. But for instance, it's called we will learn due course. So minimal model, 2D minimal model. It's for Western terminal. Sometimes for logical. So these cases, these cases, one can determine CIJK explicitly for any operator. It's called so they fit the theory called rational conformal theory. RCF, rational conformal theory. So why is it called rational? So all operator delta I is inside a rational number. And of course, central charge is also the rational number. So that this two-dimensional conformal theory is a very, very nice CFT, actually. Very nice CFT. You know, if you learn CFT, first thing you have to learn is this 2D minimal model, and next is what's the minimal vector model. But unfortunately, I'm not going to cover this course what's the minimal vector model. I only cover the minimal model. Because essentially, the minimal model captures all the typical features of the rational conformal theory. So it's called rational conformal theory because all the conformal dimension operator is rational, and central charge is also a rational number. And what we see in the minimal model case, that's the case. But for the other CFT, and given to determine this is a really difficult problem. That's what I wanted to emphasize. Some CFTs also, even if it doesn't fit this class, some CFT you can determine this one. So something is called, I think Tomoki is giving a review theory, right? In review theory, that's CFT. Actually, that's not rational conformal field theory. In 2D review theory, this one is determined. It's called DOTC formula and so on. And it's a really complicated function. So it's a beautiful function. 2D CFT, and I don't know, some people may heard of it, 4D n equal to 4 superconformal field. Apart from, so far we talk about everything 2D rational CFT, 2D review theory CFT. But apart from that, if you go to 4D, it's called n equal to 4 super YAMLs, a superconformal field theory, n equal to 4. This one can be determined. And for the other, it's mostly open. Mostly open. So unless you have a very nice structure, it's hard to determine CIJK. Even from the birth of conformal field theory to determine this guy is really difficult. But this work is already done in the 1970s. So the form of 3.2 and 3-point function is like this way up to this to determine coefficient. And this one is done by 1970 by protocol. So this one is 1970. First remember if that's the case. Let me check the date. I think I cite his paper somewhere. Yes, I think you guys have a Wikipedia, right? How old is he? I think he's almost like a 20 or something. When he was really young, I think. Like maybe younger than 20. So Porekov is one of the best quantum field theorists in our in 20th century. One of the best. Anyway, so his work, and then of course I'm going to do 1, 2, 3, and then 1, 2, 3, and 1 to 4-point function. Yes, so similar manner CIJK. Similar manner CIJK can be identified as follows. Operator OI and the operator J, and this is tau is equal to 0. Then the operator K and this. So essentially what we did is that in RD space, so we put the origin, at origin we put the OK, and we have a sphere, unit sphere at this point, 1, OJ. And then at infinity, by infinity, I put the O. So that's the picture. This is R. So this is the this can be checked by using the really definition. So this is equal to essentially is equal to limit e to delta I tau e. What I'm writing, this is k I. E, oh, sorry, this is K, and this is I. I, tau E, and then O I, tau E, and O J, 0, and then O K minus tau E, omega, and plug this one into here. and just use the conformal transformation from plane to cylinder. And then, yeah, if you take this limit, you can show that this is the really what's left. Fine. Okay, and then the question is the 4-point function. Okay, four-point function we consider is as follows. Okay, and in general dimension, this one. Again, if you use the time translations, I mean, essentially everything is just relative distance, x1, x2, x3, x4. So relative distance, again, I use this convention. And I have 4 general. Then everything, all the function depends on relative distance between operator. But if you use the other transformation of the, again, D and then what was that? D and then special component transformation, one can show as follows. This is equal to some function of G, U, and V divided by x minus 2. Okay, delta 3 and delta 4. And now, so these parts are determined by dilatation and then special component transformation. So these dependence really coming from. So these dependency is not important. And the important part is this guy. Important part is this guy. Okay, and what's U and V? U and V are dimensionless quantity called the cross ratio. So U is equal to x1, 2 squared, x3, 4 squared. And B are given by x1, 4 squared, x2, 3 squared divided by x1, 3 squared, x2, 4. So that's the dimensionless quantity. So it's just a dimensionless, its mass dimension is 0. And then it's dimensionally and invariant. So these are invariant numbers. So these are invariant. Let me erase this part. These are invariant numbers. Invariant. These quantities are the invariant under P K B. And then check. So this cross ratio is independent under the everything. So one can add any function, G or UB here. We can mark it. That's a solid. Okay. So there's no way to determine. So okay. So there's no way to determine this G of U and B. But this one can be just this will give you something called operator product expansion. So we will learn from now on operator product expansion. I call it OP. Operator product expansion provides strong constraint. So far up to this point we don't use anything except compound symmetry. So we use compound symmetry and provides strong constraint. Constraint. I mean, okay. Okay, I would say, okay, it's a bit too strong to say strong. So OP provides some constraint, okay, some constraint. And then using this constraint, one can just, in some cases, you can determine G of P. So G of, so you can determine, so to, okay. So to determine is, using OP is called conformal bootstrap. This guy, in 2 dimensions, is called conformal block. This guy is called conformal block. And the conformal block in 2 dimensions has so-called Virasoro symmetry. So the Virasoro symmetry determines this guy uniquely, but immediately, which we are going to learn from now. But for higher dimension, okay, higher dimension, it's very difficult to determine this one up until like 2010 or something like that. But then Richkoff and Simon Duffy and I introduced you to for lecture notes. They wrote the safety lecture note. Used the so-called this conformal bootstrap technique to determine this this quantity for 3-dimensional Ising model. 3-dimensional Ising model fits into so-called minimum model, the minimum model. So one can determine this one by using Virasoro algebra. We are going to introduce. But for 3D Ising model, after the onset, this Ising model is the exact solutions given by Onsaga in 1944. But there is the expectation that we can do the similar thing for 3-dimensional Ising model. Okay? But contrary to the expectation, it's very difficult to solve the 3-dimensional Ising model, like a free energy correlation function. So they're all open problem up to like 2010 or something like that. But now they have a method to do that conformal bootstrap. I think as far as I recall, they did it numerically to solve this conformal bootstrap. But now it's a really high accuracy to determine this G of the conformal block by using this bootstrap technique. Anyway, so that's if I have time, I'm going to talk about in higher dimension at the end of the lecture. I'm not sure if I can reach that. So that's the one thing. Any question on this one? So here in 2D, this is 2D. This bootstrap technique is determined by in 2D Virasoro algebra. Determine so something called so I think you open OP and so on. So the reason why I use OP and so on. So this is conformal bootstrap is again given by the first given by. So as I mentioned, this is done up to 3-point functions 1970 before I was born. So 1984, the verse of Protocol, again Protocol, so they use the following technique. So 1, 2, 3, 4. And alpha is equal to should be 1, 3, right here. 4. So essentially, so this should hold. So this is essentially the essential item bootstrap. So this tracker and graph is called operator product extraction. This is called OP. And this part is OP. So this is the essential idea to determine for one function. And in 2D Biasa algebra, I will explain how to determine this GUV in new function. That's what we want. Fine. So that's the before that we have to learn what's the operator product expansion, what is the storage product, and then what is the minimum model? How do you relate that model? That's good. Okay. So that's any questions at the moment? Okay. Unfortunately, I'm running out of time. So from now on, so far I talk about the very general things. So far I talk about all things. So anything, nothing concrete. We I just use the conformal transformation in general dimension, how the operator behave under conformal transformation and so on. And then so far at least dimensions are arbitrary. But now we focus on p equal to 2 case, and then talk about more about so equal to case. So should we talk about the issue of okay, I don't think I have time to talk about it, but in two-dimension, the primary state, there's another way to define primary state. So in conformal transformation is given by d times f of t, the holomorphic function. And then the other way to define primary state is that I think I only focus on the holomorphic part. Okay, I will take some notation now. If this is the case, it's called primary state. That's the case. And we relate So as I mentioned last time, so the K mu acts on operator Z. So this is general dimension is equal to Z. So this is the general dimension definition of primary state. But in two dimensions, there's another way to determine the primary state. This is another way. And there's a relation between, of course, the equivalent in two dimensions. The equivalent in two dimensions. This is only true for in two dimensions. In 2D, it's the equivalent. So in two dimensions, so I don't think I have time to today to explain why it is true. So we have so the primary operator. I use the O, fine. Okay, and anyways, okay, let's use my notation operator O. So if we have O of Z, and then acts on this one, then the limit take state operator corresponds to operator like this one. If you have an operator, we have a state, and then so this is called primary state. And then here, so you have an operator O, and then as you recall, so the globally defined Conformal transformation in two dimensions is Z3. And do you remember that L-1 will give you what? Translation, because I mean, this is just L1 Z up to some sign or something. And this one will give you what? Dilatation or rotation. Okay? So D over J mu. Okay? And this will give you what? This is corresponding special transformation. Corresponding to. Okay, so that's correspondence between the then we will see that this one is will give you L0 acts on this one, then you get down the O. On the other hand, it's just another by special transformation. So the primary. So this is equivalent to saying that the K analysis O. K analysis O. Okay. K. So that is equivalent to this statement. K and the primary operator is computed. And then here we just consider L1 of O is 47. Okay, so and this is level 1 descendant, and then you can consider L1 square O. But in two dimension, even many operator, so that L2 can act on O, and so on. So that will give you the this is level 1, and 2, 3 is the N. And then this will give you the so-called representation of algebra, which is called Conformal, and so on. So that's what we're going to learn. And then why this condition? So in the next lecture, I will explain why this condition is the primary, the definition will give you this condition. That's what I'm going to talk about. So from now, let's focus on Z equals to 2 case, and then just somehow develop some intuition of conformal. So that's stop here. If you have a question, just tell me.